We are on 5.6, day 9 notes, compound interest. So this is going to be some real world applications for you. Let's quickly talk about the vocabulary. So first we have A is going to be our ending balance, P is the principal or the starting amount, R is the nominal interest rate written as a decimal, T is time in years, and N is the number of times compounded per year. So our three equations that we're going to be using, first we have A is equal to P, so the ending balance is equal to the principal times 1 plus the rate raised to the power of time. So this is when we are talking about something being compounded annually. And you have probably seen this in your past algebra classes. Next, we have our ending balance is going to be equal to our principal times 1 plus the rate over the number of times compounded per year raised to NT. Okay, so this is when we talk about compound interest a specific number of times per year. And then last we have A is equal to P times E raised to the rate times time. And that is when we have something that is being compounded continuously. Okay, next we have doubling time. So doubling time is the natural log of 2 divided by the rate. So this we can only use when we are talking about something being continuously compounded. So only for continuously. Okay. And then this doubling time is talking about how long it takes to double the investment. So this is a real world application. If you invest a certain amount of money and you want to know how long until that investment is going to double, you would use this formula. Okay, so this is for how long it takes to double your investment. Okay, so let's take a second and prove this. So we use doubling time only when we are talking about continuous compound interest. So we have A is equal to P times E to the RT. So A again is our ending balance and P is the principal or the starting amount. So let's go ahead and if I want my ending amount to be 2 times the principal amount, the beginning, I'm going to write this as 2P is equal to P times E RT. If we divide both sides by P, I now have 2 is equal to E raised to the rate times time. Okay, so now I'm going to take the natural log of both sides. So I'm going to have the natural log of 2 is equal to R times T. And then let's divide both sides by R. So I'm just going to rewrite this as T is equal to the natural log of 2 divided by R. Okay, so that actually matches what our doubling time equation was. Okay, next we have nominal versus effective interest rate. So nominal is the listed interest rate. Effective is taken into account when the number of times compounded per year exceeds 1. So if compounded multiple times per year, we're going to use our ending balance is equal to the principal times 1 plus R divided by N raised to the power of N times T. So the effective rate can be found by evaluating 1 plus the rate divided by the number of times per year raised to the number of times per year, and then subtracting the 1, which we're talking about 100%, representing the starting amount, then converting the decimal to a percent. And then if compounded continuously, we use our ending balance is equal to the principal times E raised to the power of RT. And the effective rate can be found by evaluating E to the power of R and then subtracting 1, which we're talking about 100% again, representing the starting amount, then converting the decimal to a percent. Example 1, you invest $800 at 6% interest compounded annually. How much is in the account after 4 years, assuming that you make no subsequent withdrawals or deposits? All right, so since we are compounding annually, I am going to be using A is equal to P times 1 plus R raised to the power of T. Okay, so we want to know how much is in the account after 4 years. So I'm solving for A, that ending amount. We invested $800, so that's my principal. 1 plus my rate is 6%. So remember, as a decimal, that'll be 0.06. And then we are talking about 4 years. So A is equal to 800 times 1.06 raised to the power of 4. So you do want to make sure that you take your calculator out and type that in. And we end up with A is approximately 1009.8, oops, 0.98. Okay, so how much is in the account after 4 years? Approximately $1,009.98. Number 2, at what interest rate, compounded annually, will a sum of $4,000 grow to $6,000 in 5 years? So compounded annually, I know again I'm going to be using A is equal to P times 1 plus R raised to the power of T. Okay, so A, my ending amount, that's going to be 6,000. My starting amount, or the principal, is 4,000. 1 plus the rate, that's what we're solving for. And then 5 years, so raised to the power of 5. Okay, so let's divide both sides by 4,000. I will end up with 1.5 is equal to 1 plus the rate raised to the power of 5. Okay, now let's take the fifth root. So I'm going to end up with 1.5 to the power of 1/5 is equal to 1 plus the rate. Then we can subtract 1 from both sides. So 1.5 to the power of 1/5 minus 1 is equal to R. Type that into your calculator, and we end up with the rate is approximately 0.0845. Okay, but as a percent, it would be 8.45%. A bank pays 7% interest compounded annually. What principal will grow to $10,000 in 10 years? So again, it says compounded annually, so I know I'm going to be using the formula A is equal to P times 1 plus the rate raised to time. Okay, what principal will grow to $10,000 in 10 years? So my ending amount, I want to be 10,000. I don't know what the principal amount is, that's what we're trying to find. 1 plus 7%, so 0.07, and then 10 years. So I have 10,000 is equal to P times 1.07 raised to 10. Then to solve for P, I'm just going to divide both sides. So I have P is equal to 10,000 divided by 1.07 raised to the power of 10. So go ahead and pause the video, type that into your calculator, and let us know what you got for P. Okay, so you should have gotten P is approximately $5,083.49. So our principal amount, $5,083.49. Number 4, a sum of $3,000 is placed in a savings account at 6% per annum. How much is the account after 1 year if the interest is compounded annually, semi-annually, and daily? Okay, so first let's start with part A. We are working with annually, so this would give us our same equation that we've been using. A is equal to P times 1 plus R raised to time. Okay, so we are solving for A. Our principal is $3,000. 1 plus, we are at 6%, so that would be 0.06, and we are talking about only 1 year. Okay, so the amount after 1 year, if it's compounded annually, we would have approximately, you should be putting this into your calculator, but approximately $3,180. Okay, next we want to know semi-annually. So semi-annually is where n is equal to 2. Okay, so if you look back at the top when we talked about our different equations, if something is happening more than once, but it's a specific amount of times, then we use the formula A is equal to the principal times 1 plus the rate divided by the number of times, raised to the number of times the year. Okay, so we're solving for our ending balance. Our principal again is $3,000. 1 plus the rate of 0.06 divided by 2 raised to 2 times 1, since we're talking about 1 year. So if you type that all into your calculator, you end up with the ending amount being approximately $3,182.70. Okay. And then last, part C, daily, that means that our N is equal to 365. So I'm going to use the same formula as part B. So A is equal to 3,000, 1 plus 0.06 divided by 365 times 365 times 1, or raised to 365 times 1. So if you type that again all into your calculator, you end up with an ending amount of approximately $3,185.49. Okay, so here you can see the benefits of compounding daily. Number 5, a bank offers an interest rate of 7% per annum compounded daily, and we want to find out the effective rate. So if you look back at all of our formulas, if something is being compounded daily and we're looking for the effective rate, we're going to use the formula 1 plus r over n raised to the power of n. Okay? So we'll have 1 plus the rate is 7%, so 0.07. And then it's compounded daily, so that's telling us that n is 365, and then we're raising it to the power of 365. So go ahead and type that into your calculator. You should end up with approximately 1.072500,983. Okay, then again, looking at the first page of these notes, once we find that, we want to subtract 1, and we end up with approximately 0.072500983, which if we convert that to a percent, we end up with an effective rate of 7.25%. Number 6, what principal should you deposit at 5.5% per annum compounded semi-annually, so as to have $6,000 after 10 years? Okay, so semi-annually, that's n equals 2. Okay, so we are going to be using the formula A is equal to P times 1 plus R over N raised to N times T. So we want to have $6,000 after 10 years. So my ending amount is $6,000. We're solving for the principal. 1 plus the rate is 0.055 because we're at 5.5%. Compounded annually, semi-annually, so our n is 2, raised to 2 times 10. Okay, so now to solve for p, I'm just going to divide both sides. So this is going to give me p is equal to 6,000 divided by 1 plus 0.055 divided by 2 raised to 20. Okay, so that's going to give me approximately $3,487.50. Number 7, given a nominal rate of 6% per annum, compute the effective rate under continuous compounding interest. So we want the effective rate under continuous compounding interest. So look back at your formulas. Okay, it says if compounded continuously, we want to just be using the formula A equals P times E raised to the power of RT. And then to find the effective rate, we're only going to be using E raised to the power of R. Okay, So we have e raised to the power of r, which is equal to e raised to 0.06, which gives me approximately 1.061836. Again, we subtract 1, and I'm getting approximately 0.061836. Again, last step is to convert that to a percent. So we end up with an effective rate of 6.18%. And that was when we were compounding continuously. Okay, number 8, suppose that a certain principal is invested at 6% per annum compounded continuously. In part A, we want to use the rule of 70, so doubling time is going to be approximately 70 divided by R. Now here, when we have this capital R, we're going to actually be using 6 rather than changing that to a decimal. Okay, so part A, we have our doubling time is going to be approximately 70 divided by 6, and that gives us about 11.6 repeating years to double. In part B, we want to compute the doubling time using the formula, the natural log of 2 divided by the rate. This time we have the lowercase r, so we are going to switch that percent to a decimal. So I have my doubling time is equal to the natural log of 2 divided by 0.06, and that gives us approximately 11.552 years to double. And last, part C, it's asking if our answers from part A and B differ by more than 2 months. Okay, so how we want to do this is take 70 divided by 6, subtract the natural log of 2 divided by 0.06, okay, and that gives us 0.11421,365 years, okay, because we've been talking about years. But we're looking for our answer, or the question is asking if it differs by more than 2 months. Okay, so years, months, let's multiply this by 12, and we end up with 1.37 months. Okay, so the question is asking if our answers differ by more than 2 months. So no, they differ by less than 2 months.